let's take a look at the actual binomial theorem. And it is nothing new, it's exactly what we've been looking at, but now we just call it a theorem. 1 plus x to the power of n is our expansion that we saw yesterday. We could write that in some notation to save ourselves a lot of time. Our general term would just be nck times x to the power of k. K goes from 0, because the first one is nc naught, all the way up to n. And a reminder, nck, yes, it is exactly the same as combinations. So n factorial over k factorial, n minus k factorial. Note, because we're starting at 0, we'll always end up with n plus 1 terms in our expansion. Very limiting, the 1 plus x. Once again, we could extend that idea to any binomial. The only difference now is we have the powers of a and the powers of b. The two powers will always add up to be n. First little one, just going back to 11c4, back to the good old days when we didn't use calculators for this, and with that idea of rolling the factorial out. So I have 11 factorial on the top. That will cancel with the 7 factorial, because if I was to roll it out, I'd have 11 times 10 times 9 times 8 times 7 and so on, which would cancel with the 7 times 6 on the bottom. And I have a simple little one to do. And what have we got? We've got 4 2s are 8. 3 goes into 9 3 times. 3 times 10 times 11, 330. Find the value of n so that I've got this sort of equation to solve. Now, I could go back to factorial notation for this and go, n factorial and 5 factorial, n minus 5 factorial equals, and so on. Cancel out factorials and get it. But if I remember my Pascal's triangle relationship, go, hang on a sec. Surely this just means n are the two numbers at the bottom added together, because we know the symmetry of Pascal's triangle. How do I set it out? Well, I've said, well, that means that 8 must be the same as n minus 5. Another way you could say it is, well, n must be 5 plus 8, whichever way you write it. Well, n's 13 for this one. A similar idea. Sure, I could break this all into factorials and go and solve it and try and find n, or if I recognise the pattern, and this is the one where we say, well, how do we work out a particular term? We add the 2 in the row above. So the row above the 20th row would be the 19th row, so n must be 19. If I have to find a particular term, I don't want to expand the whole thing out. I'm only interested in the 5th term here. So let's write down an expression for our general term. Now I say term k plus 1, and the reason I say that is because the first term is when I substitute in naught. And I think it's silly saying the naughth term. The only reason I go k plus 1. Some people still call it k, and then over here on the right hand side you have k minus 1. Doesn't really matter. I just got this one easier. Alright, there's my general term, the first term, and then the second term. I would make the second term to the power of k, first term to the power of 11 minus k, and then we get 11ck. We want the 5th term, that's when k is 4. There it is, unsimplified. A lot of the times with these we leave those numbers unsimplified because that actually is a very large number. Let's work it out. There we go. Woo! What even is that number? Huge. Is it billion? Million? Whatever. But a very big number. We want to find the one that's independent. Again, I'll work out my general term. Independent? Well, that means it's x to the power of 0. There is no x there. So x is to the power of 0. I'm just interested in that first of all. What value of k will give me x to the power of 0? So really I'm just interested in the powers then. So 18 minus 3k must equal 0. K is 6. So let's sub it in. And there it is. I've left it unsimplified this time because again that's going to be quite a large number on top. 27 times. Not as big as the last one, but it's still a large-ish number. Find the ratio of the coefficients of x to the power of 7 and x to the power of 5. There's my general term. Just interested in the coefficients, which will be the 15ck times 2 to the power of k. The ratio, write it as a fraction, is probably easier to work out. This one I will have to put in the factorial notation. The 2 to the power of 7 and the 2 to the power of 5 is easy enough. That's just 4. What do we got? Well, 15 factorial is going to cancel. That's nice. The 8 factorial will go into the 10 factorial, leave me with 10 times 9. The 5 factorial will go into the 7 factorial, leave me with 7 times 6. Don't forget the times 4, that's 60 on 7. Okay, so playing with what we now call the binomial theorem.